imaginary, and complex numbers. In this video, we'll investigate what happens when we have negative numbers in roots. We'll introduce the imaginary number I in the imaginary number line. And we'll write complex numbers that have both real and imaginary parts. Let's talk about roots and negatives for a minute. Let's begin by taking some powers of a negative number. If the power is even, then we have the negatives canceling out. Negative times negative makes positive. And so negative 3 squared is positive 9. And negative 3 to the 4th power is positive 81. Negative 3 to the 6th power, positive 729. But if the power is odd, then we have a leftover negative at the end that makes the result negative. So negative 3 cubed is negative 27. Negative 3 to the 5th is negative 243. There's an alternating pattern of positive and negative that goes with the alternating pattern of odd and even exponents. Well, one of the basic ideas about roots is that they undo an exponent, but we've required that the base x be positive. The reason for this is that the square root of negative 3 squared turns out to be not negative 3, but positive 3. And so the inside base does not match the outside result. On the other hand, if I take the cube root of a negative number to the 3rd power, it does work because negative 3 to the 3rd power is negative 27, and the cube root of negative 27 is negative 3. They do match. So the rule works when the power and the index of the root are odd. We can't have a negative base x if n is an even number, but we can have a negative base x when n is odd. Now, another consequence of this alternating pattern of positive and negative is that we cannot take an even root of a negative number. None of these expressions has an answer in the real numbers. And the real numbers are all the numbers on the number line. So it seems as if we have no answer. If n is even, the nth root of a negative number doesn't exist. Or does it? Philosophers have argued for thousands of years about what kind of existence numbers might have. While some mathematicians thought that there couldn't be any physical interpretation of the square root of a negative number, algebraists felt the need for some number that could be the square root of a negative. So they made one up. I mean, why not? Let's imagine there is a number equal to the square root of negative 1. The number needs a name, so we'll call it I. Since the square root of negative 1 is I squared is equal to negative 1. We know there's no real number that when you square it, you get a negative, so I is called an imaginary number. Imaginary here does not say that the number does not exist. It exists the same way any number exists, whatever way that is. But it's not a real number, and it's not on the number line. It is something in mathematics that we can try to make work, though. Now, since 2i squared is 2 times I times 2 times I. 2 times 2 is 4, and I times itself is negative 1. So we have a number that when we square it, we get negative 4 for the answer, and so we think that the square root of negative 4 should indeed be 2i. And that's true for any multiple of a real number with I. When I square 3i, I get negative 9. When I square 4i, I get negative 16. And so we say that the square root of negative 9 must be 3i. And the square root of negative 16 must be 4i. You might recall that we had a rule that we've used before. If we're multiplying two roots, that's the same as multiplying the numbers inside of one root. And it works out great. The square root of 4 is 2, and the square root of 9 is 3, and the square root of 4 times 9, which is 36, is 6. And that's all true. But if those numbers inside the roots are negative, that rule doesn't hold anymore. The square root of negative 4 times the square root of negative 9 is not equal to the square root of negative 4 times negative 9, because the negatives cancel out inside the square root. You get the square root of positive 36, but over here the square root of negative 4 is 2i. The square root of negative 9 is 3i, and when I multiply that together, I get 6i squared. Since I squared is negative 1, that's equal to negative 6. But the square root of 36 is equal to 6, and so they are not equal. If the real numbers are all the numbers on the number line, where should we put the imaginary numbers? They're going to need their own number line, because every real number can be multiplied by I to give us an imaginary number. Now, if we take this imaginary number line and make it vertical, like the y-axis, we can have a whole plane of imaginary and real numbers together. The sum of a real number, like 3, and an imaginary number, like 2i, is considered to be a point in the plane. So we would write this point as 3 plus 2i. 3 is called the real part. 2i is called the imaginary part. And the whole number altogether, 3 plus 2i, is called a complex number. The real numbers are also complex numbers. Their imaginary part is 0. And all the imaginary numbers are also complex numbers. Their real part is 0. Now, the complex numbers are a number system where we can add, subtract, multiply, divide, and so forth. So we're going to explore that in the next video.